Hello, happy Tuesday. We are starting some new sections this week out of chapter 4, dealing with solving our homogeneous systems of differential equations. So what we are going to do today is something called the eigenvalue problem. And eigenvalue just means that we have like a special value. It's not actually named after someone. That beginning part of the word eigen just means that it's an important value. It's useful to us. And so what we're going to do is just kind of introduce this on the next slide here. And then we'll kind of get into examples of how we use this. So we have our differential equation. Now remember, it's homogeneous. So we don't have a g of t function over here. That g of t is equal to 0. If you needed some reminder about that, go back to section 4.3 with the definition there. So our y vector function here is some n by 1 matrix, and A is some constant coefficient matrix. And we have the dimensions here for that. So the solution, when we actually go to solve these, this is the first time we've done this, we'll take the form y1 is equal to e to the lambda t times my solution matrix here for x. Now, a couple things about lambda. Lambda is a real constant. So it's some real number constant. Okay. Now, x, this vector for x here, is some n by 1 constant vector function. Constant vector function. Just going to abbreviate that. Okay. So that's my constant vector function that we want to solve for y1 here. And in turn, we end up solving for our x constants here as well, and that helps us find our solution to our system. So basically what we're going to do is we're going to, again, just kind of going through and defining this a little bit. Let's use a little substitution into our original differential equation here. So if I find the derivative of y1 prime, then since lambda is a real constant, that derivative would look like lambda e to the lambda t. And then that's getting multiplied by my vector for x here. Okay, so we're deriving with respect to t here, so we don't have to worry about trying to figure out what the derivative of x looks like. Okay, now substituting that back up in here, let me go ahead and just write, we are going to do some substitution. So using substitution, this would look like lambda e to the lambda t times x is equal to, we have a times y. So we're going to take a times what we had here for y1, a e to the lambda t times x. Okay. So we have this common e to the lambda t on both sides here, that we can go ahead and divide that from both sides of our equation to leave us with just lambda times x is equal to our vector a times x. Now, we don't want to divide x out because x is part of our solution here. So we don't divide that out the same way we divide out the e to the lambda t. So x, since it's containing part of our solutions here, a couple things. This is kind of where the eigenvalue problem comes in. Okay, so just off to the side here. Lambda is a real constant if we refer back to that. But lambda in this problem here is what we refer to as eigenvalues. So each of those lambda are eigenvalues. Remember those special numbers. X, since it is a constant vector function, x is what we call eigenvectors. Okay, and so this is kind of the basis of our eigenvalue problem, that in order to solve these systems of differential equations that we use this eigenvalue problem and we identify eigenvalues and eigenvectors. And again, we'll kind of see some examples of that today, but then kind of throughout this week, we'll just look at what happens when those eigenvalues change a little bit. So what I'm going to do here is I'm going to go ahead and subtract this lambda x over to this side and make this a times x minus lambda times x equals 0. And we're going to go ahead and, factor out this vector function here for x. Now, what we get in parentheses here is not just a minus lambda, it's a minus lambda times the identity matrix. And so this is something, we use this idea of our identity matrix to kind of help us figure out what lambda is and then what it looks like in matrix form. So lambda times, remember the identity matrix just has ones on the main diagonal. And so if I take lambda times the identity matrix, then what I get is lambda on the main diagonal. And so I'll just do a 3 by 3 here. Okay, everywhere else you have zeros. So instead of, lambda just being some constant, we put that constant into a vector form, or I'm sorry, a matrix form here. And what we want to do is, if this is my eigenvalue equation right here, that in order to solve for x, what we really want to do is we want to take what we have here and find the determinant of a minus lambda times the identity matrix. And this is why we get this into matrix form here by multiplying by the identity matrix, is so that we can do the subtraction and then find the determinant. And what we're going to do is set that determinant equal to 0. And what this will give us, basically when we go through and we do a little solving here, is a bunch of eigen pairs. So you'll see quite a bit, some practice with this, where it says, find the eigenpairs. Eigenpairs are corresponding lambda values with the eigenvector x. So eigenvalues, eigenvectors are considered eigenpairs. So we'll come back to this idea of using the determinant as we are solving. So we're going to just do this through an example of a 2 by 2.